Hi, my name is Sadie, and this is the Identifying Unknown Hydrate Lab. In this lab, there were many concepts that we've done previously and new ones that were introduced. The first was calculating percent yield and the theoretical yield of the water in Hydrate B. Then, using the theoretical yield and our data from the experiment we made, an educated guess of which hydrate we had used. So, the overall purpose was to evaporate water from Hydrate B, calculate the percent yield of water, and then compare the theoretical yield using stoichiometry. After this was all done, we can determine the formula of the hydrate that was given. Our hypothesis before we started the experiment was if all the water is evaporated from the hydrate and closest matches to the theoretical yield, then we can identify the unknown hydrate. The equipment that was used was familiar from previous experiments. These include the evaporating dish that we used to heat up the hydrate, the wired gauze, the crucible tongues to hold the evaporating dish when it was hot, the scrupula, and the Bunsen burner and scale to measure the precise mass of the hydrate and the anhydrate.
So in this experiment, we measured out the unknown hydrate B and gently heated it over a Bunsen burner. We took the evaporating dish off the Bunsen burner a few times and weighed it to make sure that the anhydrous salt reached a constant mass and had no water left to evaporate. And we noticed that it took a long time for it to reach a constant mass. We did this so that there would be an accurate measurement of the anhydrous salt and later the calculated percent water. We decided to use evaporation so we could remove the water from the hydrate and find the mass of the anhydrous salt. This helped us answer our hypothesis because we were then able to find the mass and percent of water by subtracting the salt from the hydrate. We also chose to use a Bunsen burner instead of a hot plate because it's a rapid and concentrated heat source that made it easy for evaporation. After the anhydrous salt reached a constant mass, we weighed it and we observed that the anhydrous salt looked like white crystals. In both our trials, we used an evaporating dish that weighed 44.06 grams. And then in our first trial, the hydrate was 1.44 grams and the anhydrous salt was 0.64 grams, so the water was 0.8 grams. And then for the second trial, the hydrate was 2.31 grams and the anhydrous salt was 0.96 grams, so the water was 1.35 grams.
Conclusion. Our group was slightly off the theoretical value. Deviations may have occurred due to the possible overheating of the hydrate. Similar results were obtained by the group that selected the same hydrate, meaning overheating may have been a common occurrence. Repeated heating of various samples of our hydrate can be carried through to find a more precise value. Hydrate. So our hydrate was aluminum chloride hexahydrate. We were able to determine this by calculating the percent composition of water in the hydrate, which we found in two trials to be 44% and 42%. Aluminum chloride hexahydrate's theoretical percent composition of water is around 48%. So this is our calculations. You can see the respective data tables for trial 1 and trial 2. Here we can see the same mass of dish empty, masses of hydrates for the two. As you can see here, we carried through various heatings, coolings, and weighings in order to make sure that we have all the water evaporated to maintain a precise calculations for both trials. We then calculated the final mass of our anhydrate, 0.81 for trial 1, 1.35 for trial 2. And we also were able to calculate mass of water lost for the two trials by subtracting the beginning mass and the end mass. So here are the calculations for percent composition of water. First, we start out by subtracting the dish with hydrate mass by the dish mass to end up with a hydrate mass, which is 1.44 for trial 1, 2.31 for trial 2. We then, from the table, get the water lost mass, or the mass of water in the original hydrate, 0.63, 0.96. Then we divide 0.63 here by 1.44, multiply by 100% to get our percent composition. Same thing done here, 0.96 divided by 2.31 times 100% to get our percent composition water.
So for our post-op questions, our first question was balancing a reaction for our hydrate, which was a aluminum chloride hexahydrate, and for the products we got AlCl3 solid plus 6H2O gas, which is water vapor. For the second question, I found the molar mass of LiNO3, which is 68.95, and the molar mass of 3H2O, which is 54. Then I added those up and put 54 over 122.95 and times it by 100 to find the percent composition of water, or the water in the hydrate. And for question 3, we had to find the grams of H2O from as the missing ingredient. And then what I did was dimensional analysis to find the moles of BaCl and H2O. And for BaCl, it was 0.021 moles, and for H2O it was 0.041. And I put 0.041 over 0.021, which got approximately 2 for the coefficient for H2O and the hydrate. Then for the post-op questions, for question 4, it was the same kind of idea, but that was for COCl2, and I did the same dimensional analysis and found the missing ingredient, and for COCl2 it was 0.012 moles, and for H2O it was 0.024 moles, which got the same coefficient as the last problem, which was 2. So the chemical formula was COCl2 times 2H2O, which was the chemical formula, and then a second heating would help bring COCl2 to a final mass that was consistent and more accurate. And for question 5, it was including the same kind of idea, but it started off with having the crucible as the main mass, and then we had to find the hydrate first, and we found MgCl2, which is 0.87 grams, and H2O, which was 2.290 grams. And then MgCl2 had moles of 0.009 moles in the hydrate, and H2O had moles of 0.127. So we put 127 over 0.009, and we got 14 as a coefficient for H2O in the hydrate. So the final chemical formula was MgCl2, 14H2O. Thank you, and that's our lab report.